Imagine a world where a simple color can be the key to understanding complex concepts. This is the world of the four-color theorem, a fascinating mathematical proposition that opens the door to a realm of semantic interpretation. The four-color theorem is an intriguing problem in graph theory. It can be interpreted through the lens of existence computation, or XCR, and semantic computation, or ASCR. The goal of the theorem is to identify the minimum number of colors needed to distinguish regions on a plane, with the stipulation that no two adjacent regions share the same color. In this context, a plane is seen as a mathematical space, regions as non-intersecting shapes, and colors as distinguishing semantics. Output: existence semantics, which analyze the existence of points, lines, and planes, can help us understand the relationships between these regions. So, how can colors have an existence semantic interpretation? Consider a color C as a distinguishing semantic, used to differentiate filled and unfilled regions. When there are no lines on a plane, no divisions between regions, only one color is needed to fill the entire plane. When a line exists, splitting the plane into two regions, two colors are needed to distinguish these regions. In the case of two lines, four areas are created, each requiring a unique color for distinction. However, it's important to note that these areas are distinguished within a specific semantic range, defined by the coordinates. When three lines exist, further divisions are created, requiring additional colors. But these new regions are distinguished within a new semantic range, and the same method can be applied to determine the number of colors needed. And what about when there are four or more lines? The same principles can be applied. If a new line introduced is parallel to an existing set of lines, no new color is needed. Otherwise, the number of colors required can be determined using specific theorems. To summarize, we've used the existence computation and semantic computation framework to interpret the semantics of the four-color theorem. We've seen a plane as an existence space, regions as non-intersecting shapes, and colors as distinguishing semantics. Through analyzing existence semantics and semantic ranges, we've determined the minimum number of colors needed in given situations. We've discussed the existence semantic analysis for different scenarios, including no lines, one line, two lines, three lines, and four or more lines. In every scenario, we've determined the number of colors required and highlighted the semantic relationships between these colors. We've emphasized that distinguishing semantics happens within specific semantic ranges, a crucial point for understanding the semantic interpretation of the four-color theorem. This semantic space interpretation offers a fresh perspective that can help us better understand the four-color theorem and provides an interesting method for tackling this classic problem. By transforming the problem into an analysis of existence semantics and semantic ranges, we can comprehend the demand for colors more clearly, providing new directions for future research. This approach can also be applied to other similar problems in graph theory and combinatorics, offering a powerful tool for understanding and solving these problems. So, the next time you look at a colorful map or a vibrant painting, remember that there's more than meets the eye. There's a whole world of semantics and computations hidden beneath the surface, waiting to be explored. Isn't that a colorful thought?